managing complexity. Why is that a good thing to talk about right now? Well, OpenFOAM is big. It's really big. It now has 104 solvers, 158 utilities, and just about 1.6 million lines of code. This is the development line. This is the more detailed graph that Chris presented. But it doesn't start right at the beginning. It starts in 1994. The beginning is 1989, when I actually decided that Fortran had to go. But this is the point at which it was useful in research. This is the point at which we had students using it for purposes beyond my personal work. And it developed in this research environment up until about 1999. And then we released it here. And this development line is the uptake from companies that then contracted for the development of the code. So we've got a big change in development gradient. This is just me and some students playing around with the code, using it for a range of things. And now we've got commercial work being done on the code. And now, and it keeps growing and keeps growing. So we have continuous addition of functionality, new models, new solvers, new algorithms, pre-processing, post-processing. And we continuously develop OpenFOAM to meet the needs of the users, and the users' needs keep changing, keep developing. There appears to be no limit. There's just, when the code was about 100,000 lines, I had this feeling it was going to get to about 500,000, and that would be it. It would do everything we would want from it at 500,000 lines. We're now 1.6 million, and it's still getting bigger. I don't think we should think about there being a limit. We should think about managing the complexity to handle whatever is needed from it. But what does this mean, this increase in size? The big problem is maintenance. It's now, development is no longer the big challenge here. That adding code to it isn't the big problem. It's handling those developments within the context of a large code and making them fit and making the code reliable. Brian Kernighan famously quoted, "Controlling complexity is the essence of computer programming." This was in 1976. And this is really true. This is true. This is always true. And we must evolve OpenFOAM for it to be sustainable. So the first thing we have to do is to reduce the code load. OpenFOAM is getting larger, but can we control how large it gets? Can we handle the maintenance challenge by reducing the rate at which it's getting bigger while still adding the functionality that's required? And this is by redesign. The first thing is, the simple thing, is remove unused code. There is some code in OpenFOAM that's unused. And if you look at it, quite often it's left behind from some previous development. If you actually try to use it, you find that it doesn't work. Well, let's take it out. More importantly, a bigger effort that I'm undertaking is avoiding code duplication. Firstly, we should extend existing functionality to cope with new needs. But this itself can increase complexity. So we have to balance the code duplication from the complexity that would be we'd get from removing it. The other thing is, apart from the developments that we do at CFD Direct for the Foundation, we get contributions, and there are two basic classes of contribution. And one is contributions that come from research organizations or research individuals, PhD students. Quite often, a research project starts without any interaction with us. Some professor decides to set up a project, gets a student, They use OpenFOAM because it's a very flexible platform. It's a good choice for doing CFD research. And what do? Well, they take the easiest route and they say, well, we'll just find what in OpenFOAM is close to what we want to do. We add sources, tinker with the equations, create copies of libraries, create copies of everything until it does what they want. The problem is that at the end of that project, if they've done useful work, they might want to contribute it and say, oh, this is really great. We'll give it to CFD Direct to put into the OpenFOAM releases and walk away. But if we just took that code and put it in OpenFOAM, there would be an explosion, an exponential growth in code that would be totally unmanageable. The other major part of development is through contribution. So to manage that research development and the integration in OpenFOAM, what we have to do is redesign the code to handle the additional functionality that's been provided to us. So we take the code that's provided to us, we dissect it. We separate the new functionality from the existing functionality. We separate the transport equations into parts, into the general parts and the submodels. And then we refactor the models so that they will fit into existing libraries or move them into FE options so that they're runtime selectable. We merge the transport frameworks into existing solvers so we can extend existing solvers if that is possible. And we only create new applications, new solvers within the system if it's absolutely necessary. If we're provided a research project that adds completely different functionality that doesn't fit within this current structure, we can increase the number of solvers. The alternative part of development that we do is with collaborators. So rather than the project being provided to us at the end of the research, we are involved in the development during the project. So we have a collaboration. And that's a completely different and more effective strategy. So then developments are provided to us from the collaborators incrementally. We can review them, discuss them, and then we can merge them incrementally. This allows us to merge in frequent small commits. This is way more effective than trying to merge in single large developments and having to unpick them. So there are our developments, research developments, collaborative developments, and we have to fit them all within the OpenFOAM development strategy. And we have to do that in a manageable, sustainable way. And the way we do that to reduce the amount of additional code while maintaining complexity is by continuous redesign. To support the new functionality, improvements in reliability, usability, and interestingly, the environment in which we develop OpenFOAM isn't static. And this is great, but it has its own challenges. I mean, the C++ programming language, I started using it in 1989. It was standardized basically in 1997, and that was a good standard. But the 2011 standard that we're now using is fantastic. I mean, there's a lot of really great functionality in the language, but we can only really effectively use parts of it because we can't rewrite the whole of OpenFOAM to use all of it. We can't change everything to use in standard template libraries. I wrote OpenFOAM way before standard template libraries had even been considered. So there's a limit to what we can do, but we pick and choose. We try and do our best. We try to benefit from what the language is offering us. And all of these things to help us limit code bloat and hence simplify maintenance. I'll give a few examples of this process to illustrate the work that we've done and how it worked, how effective it is. And a good example is something I did a while back. I want to go over it again now because on this one piece of major redesign, we've had a lot of time to use it, to feel how, did we make good decisions? How does it now work for us? So the turbulence modeling in OpenFOAM, when I originally created it, OpenFOAM was originally incompressible only. I added compressibility. So I did the classic mistake of duplicated the incompressible turbulence models to create compressible versions, which was convenient to add new models, but total code duplication. It was irritating, but we could live with it. But more recently, we came to want to redesign it, think about can we avoid the duplication, what are the alternatives, particularly using new language functionality. One option is the classic option, which typically commercial CFD codes use. Only have one turbulence hierarchy because you only have one set of applications. Everything is compressible. Unless you set the density to 0 to 1, then it's incompressible. That would be one option. The other option would be to create a templated library. And we have a template parameter, which is the density, and it can be either a scalar field type or 1. The density type can be 1. I played around with these ideas. I came to the conclusion it's definitely possible, but it is a significant additional complexity, but it is a lot more flexible. But the issue came to a head when we were approached to implement multi-phase turbulence modeling. So we would like a turbulence model for each phase. So we now need the phase fraction in the modeling. It also can be compressible or incompressible. So actually, there are up to 4 possibilities. If we use the original strategy, we would end up with 4 independent turbulence class hierarchies. Okay, templating now seems very attractive. But we have to template on the density and the phase fraction types. This is a significant additional complexity, but it's got to be less than 4-fold duplication. So I undertook that work and put it in. Along the way, I kept thinking, is this the right way to go? With the complexity increasing, is this the right way to go? The usability is going to be, at runtime will be fine, but researchers, particularly adding turbulence models, will find the new structure harder to work with. It's definitely going to be an overhead. And we do think about the users and the contributors. We don't make decisions just because we feel like it or because it's entertaining. So I fully integrated it in OpenFOAM 3. But it doesn't end there, of course. You don't say, oh, it's done now. Because then other people say, well, we would like more functionality. So that's when we now come to the review part. Is that, did I make good design decisions? Having got here, I mean, I've got this templated library. Is it really as flexible as we had hoped? So first thing we had was to add viscoelasticity, which worked out actually pretty well. That went in quite well. But as soon as we had put in viscoelasticity, we were asked, well, can we make that multiphase? Can we have a VOF solver where it's viscoelastic in the liquid phase and Newtonian gas phase? So as soon as we had done that piece, it wasn't enough. So I added a VOF phase compressible turbulence models in OpenFOAM 6 to support different stress models in each phase. Was it difficult? No, it wasn't difficult. The structure really was flexible. The only mistake I made was in the name, because I had only designed the structure to do turbulence modeling. But actually, the structure is much more flexible than that. It can handle any stress model. So now we've got a situation where you can put a viscoelasticity model, you can instantiate a viscoelasticity model and run it, but you instantiate it in the turbulence model's properties. So ideally, we should rename the library, rename turbulence modeling. Now, I would like to do that from a consistency point of view, but it would be very, very irritating to the users because all cases would have to change. All input dictionaries would change name, all the parameters would change. So we haven't done it. So we live with this slight compromise that actually the code now is more general than the principles from which it started. So the bottom line is, yes, it was a successful piece of redesign. But it might not have been. And if it hadn't have been, what would we have done? Redesign it again. The other big part of redesign we've undertaken several times is Euler Multiphase. So I was involved in a research project, and I put in a very simple Euler solver to do incompressible gas bubble in liquid. And that was fine. But then there was a need for adding solid mechanics to it as well, so kinetic theory. So I created a new variant. It couldn't really be added to the old structure because that was incompressible only. So we created a new solver. And then once that had really matured, we got rid of bubble foam and only used two-phase Euler foam. And almost as soon as that had been completed, then people say, well, what about compressibility? We need that as well. So we got a new solver. Again, that couldn't be retrofitted to this solver. It had to be a new solver. And when that had stabilized, compressible two-phase Euler foam has now replaced two-phase Euler foam. And so it goes on. Well, yeah, that's all right for two-phase, but we've got lots of phases. All right, so now we've got multi-phase Euler foam. So now we've got still two solvers. Now we can do compressible, multi-phase, liquid, solid, gases, fine. But it never stops. Multi-phase never stops. Mass transfer, phase change, reactions, population balance. And in population balance, there is this method and that moment methods and class methods, and it's a nightmare. Adding all this functionality to both for two-phase and multi-phase is just impractical. So we created a structure. Not surprisingly, using templating. Templating, brilliant. And it is general and extensible and flexible and complex. But it's okay, because the people doing this kind of work, the people who really undertake this kind of work are really clever. So it's all right. They can handle the complexity, can't you? And of course, it doesn't stop there. We were asked to put in multi-phase kinetic theory, porosity, stationary phases, solidification, distributed porosity. And this may require, and probably will require, further redesign. And we'll undertake that work. But there is a big compromise here that we can't really undertake this kind of level of work with this kind of level of backward compatibility issues, usability issues, extensibility issues, just on our own and then release it and hope that everybody's happy. In the end, we do need a mechanism where we discuss with the community of contributors what we should be doing, what we should prioritize, the compromise. We can add functionality, but there's going to be a compromise. If we do this, it's going to become this much complex. If we rewrite it in this way, it'll be this much harder to work with. We've got to have those discussions, and we need a means to do that. And Chris will discuss that later. The other opportunity for reducing the code bloat in the code is going back to one of the basic principles. In commercial codes often try to create a single monolithic structure that runs anything. Just one solver that runs anything. The problem with that is that is horrendously complex to maintain, but then so they have to have armies of people working on the code. And it's also very difficult to use, and not all combinations of models are actually effective. So in OpenFOAM, we don't have that strategy. We have multiple solvers, and that's very good for very different kinds of functionality. But there's quite a lot of overlap, and it's becoming a problem now that we have 104 of them. I mean, we have a lot of code duplication between closely related solvers. We have a serious maintenance usability problem. So what can we do? Well, I take this as an example. Moving meshes used to be a specialization, is that you have solvers to do static systems and moving systems. We had a smallish number of cases that needed moving mesh capability and a very limited range of physics that needed it. That's not happening these days. Now we're involved more with the process industry. Moving meshes needs to be an option in almost any solver that can reasonably support it. So if we took that attitude and said actually put moving mesh capability in the current structure in all of the solvers, we'd end up with twice as many solvers. It's mental. But The thing with moving mesh capabilities, it's taken us a long time. We've been evolving it over a number of years. But we have now converged on a single general approach that is efficient, effective, and will handle any form of motion. And so we don't envisage changing it again. So now it's time to rationalize that implementation and merge it into the standard solvers so we can remove the current 11 dynamic mesh solvers. And that now gives us a structure where we can easily add that moving mesh capability to any additional solvers with only a modest maintenance overhead. This is a very practical proposition, and it actually didn't take that long. The other thing we could consider doing, it's less important, but we could do it, is transient solvers have evolved from a piezo-based algorithm to a pimple-based algorithm. And pimple supports both piezo and simple. So in principle, at least, the transient solvers can be used for steady simulations. There are some compromises there, but in the case of CHT multi-region foam and CHT multi-region simple foam, the code duplication between these solvers was chronic. It was a nightmare to maintain these two. So we'll put a lot of effort into merging that functionality to create a single structure that will handle the functionality of both. We could take that further. We could merge more solvers. We could merge row pimple foam and row simple foam. But should we? I mean, the code duplication here is not so bad as with the CHT case, but we could do it. We could merge the buoyant solvers. Should we do that? How about the Boost-and-X solvers? We don't really need them anymore because we have a Boost-and-X equation of state. So actually, these buoyant solvers will run Boost-and-X by choosing the Boost-and-X equation of state. But we need to spend a bit of time to see if there's any subtle difference in behavior or inefficiencies associated with that. Is it worth keeping these additional solvers? My feeling is probably not. But an idea that Will and I have been discussing recently, which I think is quite exciting, is take this idea of P_RGH, the buoyant version of the pressure used in the buoyant solvers. Would it be possible to generalize that to any pressure that is modified by some kind of body force and handle it within some kind of extended FV option? That would actually allow us to remove buoyant solvers altogether, that any solver, if at runtime you chose P_RGH, would run in buoyant mode. Again, these are quite big changes. They'll have usability changes and some kind of efficiency effects that we'll need to discuss. We really need a proper form of discussion with people that these decisions will affect, both the beneficiaries and the others. So we've made a lot of progress, and we can chart some of that in terms of maintainability from the graph of the code lines. So we have continuous development with continuous redesign to moderate how rapidly the number of lines of code increases. Starting with the creation of the release of OpenFOAM Dev here. Now, prior to that point, we see this end of this exponential growth in lines of code. We've got this flattening region where I'm doing a lot of work over the 6 months to rationalize the code. And now we're in a much more carefully organized development, maintenance, redesign strategy. So, managing complexity. So we must develop the code to meet the changing needs of the users. The needs of the users continuously increases. There is no indication that that's going to reduce or even slow down. Continuous redesign is essential. We must keep track of the structure of the code and think about how we can best modify the code, update the code to handle the new needs with a minimum additional code. over this time, and I've been working on OpenFOAM since 1989, well, firstly, it's still here. It's still growing. It's still being used. Considering I created the concepts, the field algebra concepts, the basic structure, which hasn't changed, in 1989, it has proved incredibly robust, flexible, and effective. It's still a good platform. If I was asked, if I was starting from scratch, what kind of a code would I produce? It would still be OpenFOAM, very closely. But we do need closer cooperation with the community of contributors, and we will implement a system for this. That's what I have to say.